Hey folks, today we're going to talk about Newton's second law. This is a big one. This is one that carries us through basically the entire rest of the course. And so we get an intro here and then we'll be working with it a lot in class. So we have our definition of Newton's second law. It's the law that's essentially just an equation. But in words, we have that definition. A system's acceleration is directly proportional to the net force acting on the system and inversely proportional to the system's mass. So I just want to start with what does that all mean? So acceleration is proportional to the net force acting on the system. So the net force is given by one of two symbols. I always use the first one because I like it better. But acceleration is directly proportional to the net force. Now this letter here, usually it's written like that, is the Greek letter sigma, and it means the sum of the forces. And so the acceleration is equal to the sum of the forces. That's kind of embedded into this lesson today, which can also be written as F sub net. So I always stick to this one, but you're welcome to write F net if you like the word better than the symbol. So that's the first part of the definition, basically saying if the net force gets bigger, the acceleration will get bigger also in proportion to that. So if I have a situation where some net force causes some acceleration and I double that net force, I then double that acceleration. So that's the first part. And then it says it's also inversely proportional to the system's mass. So acceleration is proportional to the inverse of the system's mass. Remember that a system can either be a single object or a collection of objects. And so the mass of the system depends on how many objects there are and what the mass of each object is. So these are the two symbols, or rather two proportionalities, that are represented by the definition of Newton's second law. And so we can combine these and turn them into an equation, and we'll go through how that works in another lesson. But basically, acceleration is equal to net force over mass. And so this is the equation that represents Newton's second law. So that's the big one. And so we're going to use this all over the place. The way that you see it written is like this: net force in the x direction equals mass times acceleration in the x direction. And so, force is a vector, and so it can point in any direction. Same thing with acceleration. And so we can have a net force in the x direction that causes acceleration in the x direction. We can also have a net force in the y direction that causes acceleration in the y direction, and then a net force in the z direction that causes acceleration in the z direction. So this equation is usually written net force equals mass times acceleration, and it implies all three of these things. In AP Physics 1 and pretty much every high school physics class, we only consider the net force in 2 dimensions. And I would say a considerable number of problems that we deal with only deal with acceleration horizontally or vertically. So we stick to 1 or 2 versions of F equals ma. Okay, so that's the equation. And then next we want to understand that because net force and acceleration are both vectors, there's a direction associated with them. And so that's very important. And so the next thing is the system accelerates in the direction of the net force. And so whatever direction has essentially the greatest force is going to be the direction where the acceleration happens. So that's kind of what we're going to talk about in the back half of this lesson is how do we know which way the net force is pointing, and how do we work with net force in general. So here we go. Okay, so I'm just going to give you some examples. We'll have some pre-drawn free body diagrams for this section. Sorry, having trouble with everything on my desk. And so here's example 1. We have this object and we have no idea what this object is doing, but the free body diagram looks like this. There is a 3 Newton force to the left, there is a 10 Newton force to the right, and the mass of this system is 5 kilograms. So we're just going to start with like a totally out of context example, because you've just learned how to do free body diagrams, and we kind of want to take it one skill at a time. So let's say we've drawn this free body diagram for this object. Notice that I drew the 10 Newton arrow much longer than the 3 Newton arrow to kind of convey the magnitudes, the relative magnitudes of these two forces. And then we have the mass. So this symbol, net force, or sum of the forces, I'm going to just explain that right here when we do things, so, or before we do this problem. So this idea of net force, we're going to take it as net force in the x direction, and then separately net force in the y direction. And so these are kind of the rules you're going to apply whenever you do net force. For net force in the horizontal direction, the two options are left and right. And so to find the net force, because the right direction is usually our positive direction, the left force is usually our negative direction, it's the right pointing forces minus the left pointing forces. Now this goes if you have like multiple forces that are left and right. It's like add up all the right facing forces and then subtract from them all the left facing forces. And so we can actually do that for this problem. We can say all of the right facing forces add up to 10 newtons, and the left facing forces all add up to 3 newtons. And so our net force in the x direction is 7 newtons. Now, because of how we like set up this equation, this answer is a vector. And because it's positive, we know that it points to the right. So we can, this is not part of the free body diagram, but we can say the net force equals 7 newtons. In other words, there's a net force because the forces don't balance. So that's the kind of leftovers. Now for net force in the y is the vertical direction. So we would want to do all of the up forces minus all of the down forces. And so this free body diagram doesn't have any up and down forces. So we would say that's a net force of 0 newtons. 0 Newton net force is very special. It means that because the net force is 0, the acceleration of that system in that direction is 0. And so we always want to consider the net force in 2 dimensions every time we do a physics problem. Oftentimes one of those dimensions has a net force of 0. So we kind of like, it's not that we stop caring about it, but it stops meaning as much to us as the direction that has an unbalanced force. So that's the idea behind net force. You always want to think of this when you think of net force. So what can we do with this information? We could say that based on this information, we could say net force in the x direction equals mass times acceleration in the x direction. And so we can now fill in 7 newtons equals 5 kilograms times the acceleration in the x direction. So if I do 7 divided by 5, I get an acceleration of 1.4 meters per second squared. So the net force on that mass causes an acceleration. And so that acceleration is based on the net force itself and the mass. Because the net force is slightly bigger than the mass, we get an acceleration that's slightly bigger than 1. So that's like a simple example. I will try and make it so that Edpuzzle doesn't make you watch the rest of this, but if you want to watch the rest of this, example 2 just deals with this in 2 dimensions. And so we're kind of at we're at 10 minutes right now, so I want to be mindful of keeping it short. Example 2 is going to be a scenario where there are 4 forces, and for simplicity, I'm going to make the arrows roughly the same. And clockwise from the top, we have 20 newtons, 15 newtons, 20 newtons, and 5 newtons. So this could be like, maybe this is a box being slid across a surface and you're looking at it from a side view. It could also be like this massive tug of war where like 4 people each have a rope that's tied to the same object and they're pulling in opposite directions. So either way, we have forces in 2 dimensions. And so every time we have forces in 2 dimensions, we want to apply Newton's second law in both of those dimensions. So I will go, and the way that I kind of want you to show your work for Newton's second law is like this. Sometimes we're going to end up having the x and y directions kind of communicate with one another through other knowledge of forces, but for now we just want to make one column for each direction. So I'm going to solve this kind of the way I want you to do it. So net force in the x direction equals mass times acceleration in the x direction. Net force in the x direction is right minus left. So I can go 15 newtons minus 5 newtons equals 2 kilograms times that acceleration. And so I can now solve this equation for acceleration. I get 10 newtons is the net force equals 2 kilograms times that acceleration. And so 10 over 2, that horizontal acceleration is 5 meters per second squared. So that's like, you can consider that to be half of my answer if the question were, what is the acceleration of this object? In the y direction, the net force is up minus down. And so you should write this, but you should also know that obviously 20 minus 20 is 0. 2 kilograms is the mass, and acceleration in the y direction is our variable. So 0 newtons equals 2 kilograms times acceleration, which means the acceleration in the vertical direction is 0 meters per second squared. Okay. So this object is accelerating in the x direction. It is not accelerating in the y direction. You would report this number as the acceleration and identify it as the x direction acceleration. It is definitely possible that you can have acceleration in 2 dimensions, especially if you take like a top-down view of something, in which case each of these accelerations would represent components of the overall acceleration. This comes up exceedingly rarely in AP Physics 1, but you want to understand that objects can accelerate in 2 dimensions, and so you would deal with them according to kind of the way we did with projectiles. And that is that.